In this chapter, we are focusing on one important aspect of stereochemistry, and this is conformations. We're talking about different arrangements of atoms in space, and these are arrangements that can be interconverted. In this video, we're going to start looking at alkane conformations, starting with small alkanes. When we think about the shape of alkanes, let's start with the shape of methane. We know that the carbon is sp3 hybridized, and so this will have a tetrahedral arrangement. And there is rotation around a carbon-hydrogen bond, but if this rotates, there's no change to the shape overall. So methane is completely described by a tetrahedral arrangement. When it comes to the shape of ethane, once again, we know that those carbons are sp3 hybridized, and so we would expect a tetrahedral arrangement. So we might draw it like this, or we might draw it like this. So these carbons are sp3 hybridized, so there's a tetrahedral arrangement when we look at the carbon, hydrogen, hydrogen, hydrogen. Tetrahedral arrangement around this carbon, around this carbon, around this carbon, and around this carbon. But what we have overall is a different shape or a different orientation in space. Here, this hydrogen, carbon, carbon, hydrogen are all in the same plane. But over here, it's this hydrogen, carbon, carbon, and then the lower hydrogen that are all in the same plane. So we have different arrangements in space between this drawing and this drawing. Because we can rotate around a sigma bond, imagine if we held this carbon still and we rotated this one, then we can convert this into this. So what we're looking at with this representation and this representation, these are different conformations. And so we have different arrangements in space. And they can be interconverted by rotation around a sigma bond. So these are the same molecule. There's the same connectivity, the same geometry around each atom. But when we're looking at the overall shape, this is where we have different arrangements in space. But because we can convert one of these into the other by rotating around a sigma bond, they can be interconverted. Therefore, these are two different conformations. Well, how can we represent different conformations? On the previous slide, we were looking at representations like these, but it's a little bit unclear whether we are just showing the shape or are we actually trying to specify the exact arrangement. So there are a couple of other ways that are unambiguously showing conformations. One of them is to use a sawhorse formula. So imagine that this is your eye, you're looking down this way. And so here is the front carbon, and then here is the back carbon. The front carbon, when we're looking at it from this perspective, there is a hydrogen going straight down. That would be this one. And then we have one that is up and to the right. That would be this one. And then one that is up and to the left. That is this one. And then on the back carbon, we have a hydrogen sticking straight up, this one that is down and to the right, that's this one, which is forward, and then this one going back, that would be over here. So we don't use sawhorse formulas when we're just talking about connectivity. These are specifically used when we're trying to show a conformation. And so we can see that this hydrogen is straight up while this hydrogen is straight down, so that the atoms in the same plane would be this one, this one, this one, and this one. If we're looking at this one over here, again, we're looking down the carbon-carbon bond. So Here is the front carbon, here is the back carbon. From the front carbon, we have a hydrogen going straight down, another one up right and up left. That's these. And then on the back carbon, we have a hydrogen going straight down, up right, and up and left. That would be these. So looking at the original structures, it's not clear whether you're trying to show conformation, but if you use a sawhorse formula, then it's definitely showing conformation. So you might come across sawhorse formulas, but a much better way to show them is using a Newman projection. So once again, we are looking down this carbon-carbon bond, and we have our back carbon and our front carbon. With our front carbon, we have a hydrogen going straight down, a hydrogen up and to the right, and a hydrogen up and to the left. And then on our back carbon, we have a hydrogen that's going straight up. Now make sure that these are drawn not all the way back to the middle, but to the outer circle, because this is what represents the carbon. So then we have a hydrogen here and a hydrogen here. For the other one, once again, we're looking down this bond, so we can have our back carbon and then our front carbon. Our front carbon has a hydrogen down, up and right, up and left. And then our back carbon has a hydrogen down. So these are right on top of each other, up left and up right. So Newman projections are very, very commonly used to represent conformations. So I want you to be familiar with them. I want you to be able to draw them, and I want you to be able to interpret them. What does this mean? Now, over here, it was really hard to draw the second set of hydrogens because they're overlapped right on top of each other. And we call this an eclipsed conformation. So when in this case, the carbon-hydrogen bonds on the front carbon are exactly overlapping the carbon-hydrogen bonds on the back carbon, that is eclipsed. In contrast, over here, if we look at the angle between the blue hydrogens, the red hydrogen exactly splits that angle in half. And so what we have here is a staggered conformation. So staggered and eclipsed conformations are possible. Okay, let's continue to talk about the eclipsed and staggered conformations. Now, we can define what's called a torsional angle. So the torsional angle would be the angle between this carbon hydrogen and this carbon hydrogen. So we think about the plane that holds this one and the plane that holds this one, and they are 0 degrees away from each other. Over here, if we are looking at this bond compared to this bond, here we have an angle of 60 degrees, right? Because going all the way around the circle would be 360 degrees, so 1/6 of the way would be 60 degrees. So an eclipse conformation has a torsional angle of 0 degrees. A staggered conformation has a torsional angle of 60 degrees. In addition to eclipsed and staggered conformations, there is an infinite number of conformations in between. These are the only ones that get names. So we need to think about steric strain. And we're going to see several types of steric strain. So steric strain, it is some kind of instability that's brought about by the location of different atoms. So what we have here then is the first type of steric strain called torsional strain. So this is the decreased stability of a molecule when the bonds are not staggered. So in this staggered conformation, the torsional angle is 60 degrees. There is no torsional strain. In an eclipse conformation, where the torsional angle is 0, this is where we're going to have the maximum amount of torsional strain. And we have this strain because remember what this line represents. This is shared electrons, this is shared electrons, and so we have these negative charges that are aligned with each other. So the negative charges are repelling each other. So if we are in this conformation, then that brings with it some instability. So if a particular molecule in a particular conformation has a torsional angle of 60 degrees, then there is no torsional strain. If the torsional angle is anywhere from 0 to 59 degrees, then there is some torsional strain, which makes that molecule less stable. Now here we have an energy diagram showing rotation around the central carbon-carbon bond in ethane. So here we have our torsion angle going from 0 all the way up to 360. And over here, we're looking at increasing potential energy in kcals per mole. And here it's in kilojoules per mole. So looking at this conformation and focusing on the two red atoms, that bond angle is 0 degrees. And then imagine if we hold the back carbon still and we rotate around the front carbon. Here we have the maximum torsional strain, which is why this has the highest energy. As we're going from 0 degrees towards 60 degrees torsional angle, then the torsional strain is going to decrease. It reaches a minimum when we get to our first staggered conformation. So the staggered conformation, where there's no torsional strain, that is at a minimum. If we continue rotating our front carbon, now we are decreasing our torsional angle, so we are increasing our torsional strain until we get back here to another eclipsed conformation where we are at our maximum energy because of the maximum torsional strain. Continue rotating and we get to another staggered conformation, low energy. Continue rotating, we get to another eclipsed conformation, maximum energy. Continue rotating, we get to another staggered conformation, minimum energy. And finally, continue rotating, and we get back to our original conformation where we have an eclipsed conformation, and so we have torsional strain. So the difference in energy between the low energy conformations and the high energy conformations, these differ by 2.9 kcals or 12 kilojoules per mole. So this still means we have free rotation. So at room temperature, about half of the molecules in a sample are going to go from one staggered conformation to another staggered conformation in 10 to the negative 6 seconds. So the rotation is really fast. This 12 kilojoules per mole is not really a barrier. So unless you had a sample that was really, really, really cold, in general, the molecules will have enough energy to overcome this barrier. And so we talk about having free rotation around that carbon-carbon bond. Now, this is something that you may have seen in Gen Chem. This is called the Arrhenius equation, and this is the rate constant K. So this tells us how quickly a reaction or some change is happening. A is the Arrhenius constant or Arrhenius factor. EA is the activation energy, R is the gas constant, and T is temperature. So what we see is that the rate is proportional to the temperature. So looking at this diagram, here we have our energy increasing toward the right, and this is the fraction of molecules having a particular energy. So the blue curve is at low temperature. So most of the molecules have this much energy, but there are some molecules that have higher energy. And so a few of those molecules will be able to overcome a particular activation energy. But at higher temperature, this is the pink curve, most molecules have more energy, and then there will be more molecules that have enough energy to overcome the activation barrier. So in the case of rotation in ethane, this particular activation energy is going to be really low. And so even at room temperature, if we consider low temperature room temperature, or if we have it at elevated temperature, lots of molecules are going to have enough energy to overcome that activation barrier. And so we have free rotation.